Okay, so we're very happy today to have Zeyu Guo from University of Haifa. He's going to talk to us about efficient list decoding and also introduction to AG codes.
Okay, thanks for the introduction. This is John to work with my postdoc advisor, Nobel Zeyu. Yeah, this talk, I'm going to talk about the error correcting codes that were introduced by Hamming and Shannon in 1940s. So it's used widely in communication to make the communication more reliable. So the idea is that when you send a message through a noise channel, then the message may get corrupted by the noise, so the receiver may not receive the correct message. So instead of doing that, we first send a message to an encoder, which turns the code word into turns the message into a code word, and then we send the code word through the noise channel. And when the decoder receives the code word, it recovers the original message and sends it to the receiver. This makes the communication more reliable. And error correcting codes are used everywhere in the real world. For example, when you make a phone call, when you download something from the internet, even this Zoom talk is made possible only because we use error correcting codes. So they are very important, and we want to study them mathematically. And this is here's a definition for error correcting code. So code is you can think of it as a map C from sigma to the k to sigma to the n that maps messages to code words. Sigma is a finite set of symbols, which we call alphabet, and k is the message length, and n is the code word length. And codes have some important parameters. One of the most important one is rate for the code, R, which is defined to be k divided by n, and it measures the redundancy in coding. Another important parameter is the minimum distance, defined as follows. So for two vectors, x and y, we define the relative distance to be the fraction of coordinates where x and y differ. So it's a number between 0 and 1. It's also called the relative Hamming distance. And then the relative minimum distance of the code C is defined to be the minimum of the distance between x, y, where x and y range over the pairs of distinct code words from C. We call the minimum distance delta. So now we can talk about decoding. The traditional notion about decoding is unique decoding. Let's consider a model where the adversary could corrupt a p fraction of coordinates. And then given a received word y that comes from some code word x, the decoder wants to find the unique x such that where it comes from. And because we know the adversary corrupts at most p fraction of coordinates, we know that distance between x, y is at most p. So as shown in this picture, we are looking for x in the Hamming ball of radius p is centered at y. And in order for x to be unique, we must have the radius p to be bounded by half of the minimum distance delta. Otherwise, x may not be unique. Okay, this is a unique decoding. And list decoding is a relaxation of unique decoding. It's introduced by Elias Rosenkranz in 1950s. And still, the adversary could corrupt the p fraction of coordinates. And here, instead of looking for unique x, we allow the decoder to find a short list of x, such that the list contains the transmitted code word x. So because we give up uniqueness, now we can make the radius larger. We can make p larger, and we can correct more than half the half delta fraction for errors, as shown in this picture. So the Hamming ball will contain more than one code words, but that's fine because we don't require any unique. So this is list decoding, and list decoding has some advantage over unique decoding. Encoding theory is a very fundamental concept, and it can be seen as a bridge between so-called Hamming channel and the Shannon channel. And even if even if the list size may be greater than 1, sometimes we can use the context information or set information. So it's very important in coding theory. But I want to talk more about the advantage in TCS. So here's the intuition why this decoding is useful in TCS. Suppose we define the relative agreement to be 1 minus the minimum distance, just the fraction of coordinates where x and y could agree. And then for unique decoding, because we have seen that the minimum distance between x and y must be bounded by the distance between x and y has to be bounded by half of the minimum distance in order for so that x can be so that x will be unique. So and delta is the minimum distance delta is a number between 0 and 1. This means the distance can never go beyond 1/2. So this means if you look at the agreement, the agreement has to be at least 1/2 for unique decoding. Otherwise, actually will not be unique. So the agreement can never be subconstant. Has to be at least 1/2. But for list decoding, because we give up uniqueness, we can have the distance go beyond 1/2 and even very close to 1. This means we can address the case, even the case that the agreement is very small. So even if the agreement is small, we can still recover not the unique x, but the short list of x. And in complexity theory and other areas in TCS, the fact that we can address the very small agreement is very important. And the downside is that we no longer have a unique x, but only a short list of x. But this is not usually not a problem, because even if you have a short list of x, as long as it's short, like polynomial size, then we can just, for example, we can just enumerate all of them one by one. So in TCS, the uniqueness is not important, but it's very important to keep the agreement small. And this is the intuition why list decoding is more important than unique decoding in many applications. So here I list some applications in TCS. List decoding is used in cryptography to prove hardcore predicates. It has applications in learning theory to learn Boolean functions, decision trees, DNF and DNFs. And in complexity theory, it has applications to average case to worst case reductions, hardness amplifications, randomization, construction of random generators, etc. So given that list decoding is very important, we want to construct a good list decodable codes. So what do we want? Ideally, we want a code of rate R such that the code is decodable up to the radius 1 minus R. This is the best one can hope. And we call this list decoding capacity. We also want the code to have small list size and also hopefully small alphabet size. And the code should be explicit, meaning that the encoding map should be computable in polynomial time, and should also be efficient list decodable, meaning that we have an efficient list decoding algorithm. So, sorry, is there so the list decoding, so if we don't want the code to be explicit, then the list decoding, so-called list decoding capacity theorem, gives a very good list decodable code. It states that for any R and epsilon between 0 and 1, there exists a non-explicit code of rate R that list decodable up to radius 1 minus R minus epsilon. And the list size is linear in 1 over epsilon, and the alphabet size is exponential in 1 over epsilon.
Is this true for most codes, or is this true like with probability 1 over choice of a random code?
Yes, this is proved by probability method. So you just take a random code. Mm-hmm. However, so this is a very good code, but it's not explicit. We want to find the explicit code. The question is, are there explicit capacity achieving this decodable code with similar parameters?
And like another question, how bad, if you want like codes that are particularly bad as list decodable, is this a trivial question to construct? Of course, fixing other problems, so making everything good except for, say, list size, or
Okay, can I repeat the question? What?
Yeah. Is it somehow non-trivial to have codes that are bad? So you're saying most codes are good.
Oh.
I want to find codes that are good with respect to all parameters except for one.
Reed-Solomon.
But is this an extremal case, or or is this the easiest case?
So what you want bad codes? I mean, for bad codes, it should be.
I want codes that are good for all purposes except for list size. Okay, so they're good in terms.
Reed-Solomon is amazing for anything you want except list decoding.
Okay, good. And this is the easiest or most extreme example of this kind, or?
For me, Reed-Solomon is the easiest, but I don't know it for you.
No. I mean, just in terms of proving that it's bad. Like, okay, so I'm not on top of all the recent results, but many questions about list decoding, even combinatorial list decoding of Reed-Solomon codes were not solved 10 years ago, right? So, yeah.
So what is the list size for Reed-Solomon?
For Reed-Solomon, I think it's not known to be capacity achieving. It even if you allow the list size to be relatively large, it does not achieve 1 minus r. I'm going to talk about this in the next slide. Okay. But yeah. Okay. So okay, so this is a Reed-Solomon codes. In case you don't know, so it's defined over a field, find a field FQ, and it's given by encoding map that maps a polynomial f of degree less than k to a vector of evaluations at n distinct evaluation points from the field. And this is one of the most important codes, most well-studied codes. And Guruswamy and Sudan in this celebrated work show that the Reed-Solomon codes are efficiently list decodable up to the radius about 1 minus square root of r. It's also known as the Johnson bound. But the capacity is 1 minus r. So, and most there are works showing that most Reed-Solomon codes are list decodable beyond the Johnson bound. By breakthrough, there's a breakthrough by Rudra and Wouters, and I also have a recent paper on this. So, but however, none of these results achieved the capacity.
Maybe let me sharpen my previous question. If you want to design a code like a non-algebraic, just taking a random code and making it worse in some way, if I just want to prove the existence of a code that has the same type of features as the Reed-Solomon code, is this an easier goal? Do we need algebra for that? That's my question. If I just want to prove the existence of a code, right? So pick codes from a distribution which is not a uniform distribution that have the same type of characteristics of Reed-Solomon codes. So do you need algebra for that, or can you build it combinatorially? That's my question.
If you don't want explicit, then the theorem.
No. So, but Yuval, I think usually in coding theory we want a code with good properties, not code with bad properties.
No, sometimes no. For crypto, you
want bad properties.
No, it's not bad. What do you mean? Having big list size, you take sides here. No, come on. Let's be.
But you want good rate and distance, but bad list.
Yeah. No, yeah. I want something that has the same combinatorial list decoding properties as Reed-Solomon codes without algebra. It's a well-defined question. I mean, you can complain that you don't like it, but you can't complain.
No, I like it.
Yeah.
I don't know. Yeah.
Or after the talk, though.
Yeah.
Yeah. Okay. I'm not sure. Yeah. Okay. Yeah, I was thinking about this. I'm not sure. So, okay. So this is Reed-Solomon code, and it's very simple, but it's not known if it can achieve the capacity. And so the first explicit code that achieved the list decoding capacity is known as folded Reed-Solomon codes. It's constructed by Guruswamy and Rudra in their famous paper. They can achieve the list decoding capacity 1 minus r minus epsilon, and this code is just obtained from the standard Reed-Solomon codes by combining m symbols into one, where m is a parameter called the folding parameter. So this is an example where m equals 3. So here it maps f to this code word where each column is a new symbol. So you can think of it as like 3n evaluations, and you combine each 3 evaluations into one symbol. Here gamma is a generator of the multiply group.
So each column is one symbol, right?
Each column is one symbol, yeah.
And if you look at interleaved Reed-Solomon codes, I guess that folded is kind of a special subcode of interleaved Reed-Solomon codes, right? So in interleaved Reed-Solomon codes, you can allow every, say, row to be a code word of a Reed-Solomon code, and you consider a column to be a symbol. So are similar, is this well understood, the list decoding of this interleaved Reed-Solomon case?
But by interleaved, you just mean folded, or what do you mean by interleaved?
Folded here, you're given a very specific, so let's say that you have this matrix whose rows are Reed-Solomon code words, arbitrary Reed-Solomon code words, in a fixed Reed-Solomon code. The interleaved version will have code words be matrices where each row is a Reed-Solomon code word, and a column of a matrix is one symbol, like here, right? A column of this matrix is a symbol of the code. So now I'm just relaxing this specific structure by allowing every row to be an unconstrained Reed-Solomon code word. So my question is, it's kind of this, here you're using this structure, right? The dependence to get the list decoding. My question is, yeah, maybe the question doesn't make sense. Maybe my question is clearly more.
I don't know. It's very simple.
Yeah, my question is that doesn't make sense. Okay, please go on. Yeah.
Okay.
Just a brief thing. The interleaved thing, it seems like the list decoding of this is more difficult than standard Reed-Solomon codes, and here you have a special structure for these columns. Okay, that helps you.
Okay, so for this code, the alphabet size is n to the 1 over epsilon square. So because for standard Reed-Solomon code, the alphabet Q has to be at least n, and you do folding, so now the alphabet size is larger. And the list size originally also depends on n, but in the paper by Kopati, Zeyu, Saraf, and Wouters, they improved the list size to 1 over epsilon to 1 over epsilon. So now it only depends on epsilon. It's constant effect.
Sorry, is gamma just a fixed field element that's part of the specification, like the interpolation points? I'm asking what is gamma? Is it just a
gamma is a generator of the multiply group of the and you need to choose alpha, alpha2, alpha1, alpha2 through alpha n, so that all these 3n evaluation points are distinct. I mean, you don't want to choose alpha1, alpha2 to be gamma alpha1.
Yeah.
Otherwise, yeah. Okay, so you can see that. So folded Reed-Solomon codes achieve the capacity, but the alphabet size. So recall that in the capacity, in the theorem about the non-explicit codes, we can get the alphabet size and list size both constant, depending only on the epsilon. But here, the alphabet size still depends on n. That's one downside of one drawback of this folded Reed-Solomon code. So we hope to get to reduce the alphabet size constant. And here are some constructions that achieve this. So one construction given by Goswami and Xing in 2013 is a subcode for algebraic geometry code. It has alphabet size 2 to the tilde O 1 over epsilon square, and the list size is singularly exponential 1 over epsilon times triple exponential in log n star. Because log n star grows very slowly in n, this one is slightly super constant in n, but it's still super constant. And actually, our work depends heavily on this one. So, and another construction is given by Kopati, Zeyu, Saraf, and Wouters. They use the idea of multi-level concatenation for the Reed-Solomon codes, plus the expander-based amplification. So alphabet size is 2 to the poly 1 over epsilon, and the list size is a tower in 1 over epsilon. Maybe it's possible to improve it to double exponential. I don't know, but the encoding time is poly n times 2 to the poly 1 epsilon. So when epsilon is small, you can argue that this is still not polynomial time. So here's our result.
Just a question. So sorry for interrupting before your results. So about these previous results. So some of these results on say algebraic decoding, you have simple abstraction of what is special to Reed-Solomon codes. They have this multiplication property that if you take the Schur product or the code spanned by pointwise products of pairs of code words, it has non-trivial minimal distance. So that's kind of a generic property of codes that suffices for the Bergkamp-Welch decoder. My question is whether in this domain, and this is a property that is shared by Reed-Solomon codes and algebraic geometric codes. So you can, for instance, you can derive efficient decode. You can apply the Bergkamp-Welch decoder to algebraic geometric codes just knowing that AG codes have this simple abstract property without knowing anything about how these codes are constructed or why they work. My question is whether there is any abstraction if you go back to the previous construction that works with folded Reed-Solomon codes. Is there any kind of algebraic abstraction of what is the property of these codes for which, what is the property of folded Reed-Solomon codes in the same way that I just said it quickly, what is the abstraction of the property of Reed-Solomon codes that makes the Bergkamp-Welch work? And then you can derive as a corollary that algebraic geometric codes also can be decoded with the same decoder. My question is whether there has been an abstraction in the literature, or are these results just solve the problem for scratch, or they define an abstraction and then show, hey, we can realize this abstraction? That's my question.
So you want some abstract property that?
Yeah, it exists for, like Ron Meir used it to build TCPs. So to understand which kinds of code. What are the properties of the code? In this case, my question, I know the answer to this question in the context of classical decoding. And my question is whether in the context of list decoding, such an abstraction has been made. Maybe I assume that not, because these people are very well familiar with abstractions. And I
can only say for all those codes that achieve the capacity, they all have some common property that somehow it involves automorphism of the fields. Like in the folded Reed-Solomon code, there's this automorphism, and that is used in folding. Our code is also this Frobenius automorphism. So somehow there is also they appear in all this paper, in all these codes that achieve the capacity. There is a automorphism of the field. I'm not sure if it's necessary, but it's just
okay. No, that's good enough. Yeah. Thanks.
Okay. So this is our results. We show that there exists codes of rate R that's list decodable up to radius 1 minus R minus epsilon. So it achieves the capacity, and this size is exponential in poly 1 over epsilon. Alphabet size is exponential in tilde O 1 over epsilon square. And moreover, it's explicit in the sense that the encoding time is fully polynomial in both n and 1 over epsilon. And also, you can do efficient list decoding in the following sense. So you can think of the list, the space of messages is a vector space over a finite field. Then for any given received word, the list of candidate messages is contained in a subspace of dimension, a small dimension, bounded by poly 1 over epsilon. And also the basis of this subspace can be computed efficiently. But if you want to compute the whole list, it will take time, exponential in poly 2 to the poly 1 over epsilon times poly n. So it depends exponentially 1 over epsilon. But this is inevitable because our list size is already exponential in poly 1. So unless you improve the list size, this dependence is inevitable.
I see. So it's still open to improve the 2 to the poly 1 over epsilon to poly 1 over epsilon. That's really good.
So actually for all explicit codes, like folded Reed-Solomon codes, best is also exponential in 1 over epsilon. And our proof heavily depends on the paper by Guzman and Xin that uses AG codes. And the one key new idea that we introduce is a notion called the BTT subspace. So let me, before presenting the construction, let me first explain this notion of BTT subspace. So we say a matrix is a KMR, a block triangular topoless or BTT matrix over field F if it's a Km by Kr full rank matrix over field F that is both block triangular and both topolets as a BTT block matrix. So this is example when K equals 4. It's a 4 by 4 block matrix where each block is a M by R matrix and has full rank, meaning that which is equivalent to M1 being full rank. And you can see it's a block triangular. So if you write it as a block matrix, it's triangular. And it's block topoless, meaning that each diagonal, for each diagonal, the blocks have the same value. So this is a definition of BTT matrix. And we define a BTT space, subspace, to be the image of the BTT matrix, regarded as a linear map. Okay, so this is a definition of BTT matrix and BTT subspace. And now I'll give an overview of our construction. So our construction, our code has alphabet sigma, which is fq to the m, where q is probably 1 over epsilon, and m is O1 over epsilon square. So in particular, the size of sigma is 1 over epsilon to 1 over epsilon square, which depends only on epsilon. And our construction has 2 steps. First, we construct a preliminary code that is list decodable, but the list size is not constant. But we can show that the list is contained in a small BTT subspace, it's not. But the dimension is not constant. And then in the next step, we construct an explicit subspace of low codimension, the subspace of the message space of low codimension, which has the property that it evades any BTT subspace. So it's meaning that its intersection with any BTT subspace is small, actually it has constant size. And then restrict the message space of the preliminary code to this evasive subspace. And then after the restriction, we know that the list size after the restriction must be contained in the intersection of a BTT evasive subspace and a BTT subspace. And because of the evasiveness, we know that the list size must be constant. So this is an overview of our construction. And so let me first explain the first step where we construct the preliminary code. And we follow the construction in Guzman and Xin, which use AG codes with subfield evaluations. But to make the talk elementary, let me work with pretend that we use the Reed-Solomon codes with subfield evaluations. The ideas and proofs are very similar. So later I will explain more about AG code, but for now let's assume we are using Reed-Solomon codes. So recall that this is the Reed-Solomon code is given by the encoding map that maps a polynomial into a vector of evaluations. So what's the Reed-Solomon code with subfield evaluation? It's simply a Reed-Solomon code defined over extension field fq to the m. So it's just a Reed-Solomon code defined over extension field, but we still want the evaluation points to be from the base field fq. So this is what we call Reed-Solomon code with subfield evaluations. And for Reed-Solomon code with subfield evaluations, we can show that the list is always contained in the BTT subspace. And here is how we find the BTT subspace given the received word y. So given y, we want to find the BTT subspace containing the list of all messages f whose corresponding code words are close enough to y. And it can be shown that we can find, given y, we can find the low degree multivariate polynomial q over the extension field fq to the m, over this univariate polynomial ring, such that q it can be think of as a relation that f and its conjugates must satisfy. So this equation holds. And this can be shown, and if you have not seen this before, you just have to believe me that you can find this Q. Q can be found by interpolation, by solving a list of a system of equation systems, and that's called the left-hand side of this equation, Q star of f. Now we know Q star of f is 0, but at the same time we know that Q star of f is a polynomial. So when we say it's 0, we get not only one equation, we get a collection of equations by equating its coefficients to V0. So we get collection of equations from this above equation, and it can be shown that all these equations are actually linear equations. So if we write down the matrix that express this in the system of linear equations and call it M, then we can show that M is actually a BTT matrix. So as a conclusion, we know that F is containing a kernel of M. Actually, more accurately, it's in the Fn shift of the kernel because the equations are not homogeneous. But ignore this difference. Let's just pretend that F is in the kernel for simplicity. And this a basis of this kernel can be found efficiently by just writing down the matrix M and solving the linear equations. And so we have found a BT a subspace that contains F, the list of all possible F, and we need to show that it's a BTT subspace. And we show that the BTT matrix has this property that its kernel is a BTT subspace. Therefore, kernel of M is a BTT subspace. Note that this is not automatic because we define the BTT subspace to be the image, not the kernel. But actually, we show that the kernel of BTT subspace, BTT matrix is also the image of another BTT matrix. So this is how we show that the list of F is contained in the BTT subspace. And so far, we're using Reed-Solomon codes. But Reed-Solomon codes has a downside, which is that you have, in order to get n distinct evaluation points, you must make the field size at least n. But we want the alpha byte size to be constant, independent of n. So instead of using Reed-Solomon codes, we use AG codes with subfield evaluations. So I tried to give an introduction about AG codes. It can be seen as generalization of Reed-Solomon codes. And if you think about the evaluation points of Reed-Solomon codes as points on a line, you can think of AG codes as more general, where the lines are replaced by so-called algebraic curves. And a remarkable thing about AG code, this algebraic curves, is that even if you fix Q, find a field FQ, you can still get arbitrarily many evaluation points, as long as you use a complicated enough algebraic curve. In particular, if you use we use the explicit curves from the so-called Garcia-Tiktanov's tower, and this was also used in the Goswami-Singh paper, and our treatment follows them almost identically. So we just replaced Reed-Solomon codes with AG code, and all the analysis still hold. It's very similar from Reed-Solomon codes. And here I want to give you more intuition about AG codes because you've all said this is going to be introduction, so I don't want to disappoint you. So so here's the intuition about why AG codes generalize at Reed-Solomon, how they generalize Reed-Solomon codes. So if you think about Reed-Solomon codes, there are two simple properties that are used in Reed-Solomon codes. The first property is that if we denote by V the space of degree D polynomials, then any non-zero F from V has at most D zeros. So low degree polynomial cannot have too many zeros. This is first property. And second property is that dimension of V is D plus 1. So these are the two important properties, that very simple properties that are used. The first property can be used to give a lower bound for the minimum distance, and second property can be used to give a lower bound for the rate. And the reason AG codes can generalize Reed-Solomon codes basically boils down to the fact that these two properties can be generalized. So for the first property, we have an analogous space V for the space of degree polynomials. And this space is called the Riemann-Roch space, and still has the property that for any non-zero F, it has at most d zeros. The second property has to be weakened. So originally we know that dimension of V is d plus 1. So space of degree d polynomials has dimension d plus 1. And for AG codes, it has to be replaced by the weaker property, where the dimension is between d plus 1 and d plus 1 minus g, where g is something called the genus, which is the invariant depending only on the curve that we use. So because this property is weaker, if you do the same analysis, this g introduces the error term in the analysis. Therefore, we don't want this g to be too large, otherwise the AG codes cannot be used. It's not useful. And fortunately, it can be shown that there exists explicit algebraic curves where we have a good upper bound for g. In particular, in the Garcia-Stickton tower, that we have a good upper bound for g. So then, because we have these two properties, everything about resolvement codes basically can be also hold for AG codes. Okay, so this is the intuition about AG codes, and we use this to construct the preliminary code, and this is the first step. Next, I'm going to explain the second step, where we construct the so-called BTT evasive subspace. So here's the formal definition. It's a subspace such that for any BTT subspace, the intersection is small. It's bounded by a parameter S. And we want to construct explicit BTT evasive subspace. And here's what we can achieve. We show that there exists explicit BTT evasive subspace such that the codimension is small. So the dimension for the ambient space is k times m, and we show that our BTT evasive subspace has codimension epsilon times km. So if you restrict to this subspace, because it's dense, it's only reduce the rate by epsilon, which is not important, which is okay. And on the other hand, the parameter S is at most the poly 1 over epsilon, and it controls the list size. So as I explained before, we restrict the message space to this BTT evasive subspace, and then reduce the list size to Q to the S, which is constant depending only on epsilon. And this is the final code we use. And so it remains to construct this BTT evasive subspace. And to construct it, we have to introduce the relaxation of the BTT subspace, which is called the periodic subspace. It's already used before in Grossman machine paper. So here's what the definition of what periodic subspaces are. So the left-hand side, this picture is a BTT subspace, a 4x4 block matrix. And the periodic matrix is a relaxation of PTT subspace, where we only require so it's still block triangular, but we only require the main diagonal, the blocks on the main diagonal to be the same. For those blocks off the main diagonal, we don't require anything. So this is definition of periodic matrix. It's a relaxation of BTT matrix. And then you can define periodic subspace to be the image of periodic matrix. And you can also define periodic evasive subspace in the same way. And because from this picture, you can see that the BTT matrix is also a periodic matrix. So BTT subspace is also a periodic subspace. Then, therefore, if we can evade periodic subspace, we can also evade BTT subspace. So conclusion is that a periodic evasive subspace is also a BTT evasive subspace. It's the same parameter. And therefore, in order to construct BTT evasive subspace, we just need to, one way is to construct a stronger periodic evasive subspace. And our starting point is this result by Goswami and Kopati, based on something called the explicit subspace designs, which shows that we can indeed construct the explicit periodic evasive subspace that has a low codimension. So it seems that we have a evasive BTT subspace construction. However, the problem is that if we apply this theorem directly, it only implies BTT evasive subspace for k that is polynomial in the alphabet, in the size of polynomial in Q. But in our case, because we use AG code, Q is polynomial in 1 over epsilon. So we could only handle k up to poly 1 over epsilon, which is too small, because in general we want k could be linear in n, the code length. So this is too small. It doesn't work if you apply the theorem directly. And here's a new idea introduced by Goswami and Xin called composition. So they put a composition lemma which says if you have a periodic evasive subspace W and another periodic evasive subspace W prime, then you can compose them to get a new periodic evasive subspace W. And the composition is defined to be W to the K intersect with W prime. And we call W the inner subspace and W prime the outer subspace. You can think of this as an analog of concatenating two code words, an outer code and with the inner code. And we can use this composition lemma to construct, and then use the Goswami-Kobati theorem to construct the explicit constructor in the previous slide to construct the outer subspace, so that it remains to construct the inner subspace. And this idea has an amazing effect that it reduces K to K prime, because to much smaller parameter K prime of order only logarithmic in K, because now we only construct the inner subspace. But the downside of this is that it increases the parameter S to poly S. And we can continue this idea, repeatedly using this idea, compose it many times. And it takes log n star times to reduce K to constant. And this is indeed the construction used in Goswami-Xin paper. But because each time when we do composition, it increases S to poly S, and we do it a super constant number of times, in the end, this size is super constant. It depends on log n star. So to get constant list, we need some new idea. And here we give a better construction with some new ideas. First, we extend the composition lemma by observing that if the inner subspace is only BTT evasive, not periodic evasive, not necessarily periodic evasive, then the composed subspace is also BTT evasive. And because our final goal is construct a BTT evasive subspace, so it's okay. It's good enough for the inner code to be BTT evasive. And another idea is that we only apply composition lemma twice to reduce K to O log K. And then for the inner subspace, instead of keep composing it, we use brute force search to find a good non-explicit inner BT evasive subspace. And normally the brute force search is expensive, takes exponential time, but here, because you reduce K to log K, we can afford the brute force search. So basically, this is a general idea that how it works. And still, we need to show that the existence of good non-explicit inner subspace, and the existence is guaranteed by the probabilistic method. And I also want to remark that the existence crucially uses the BTT evasiveness, not periodic evasiveness. Because if you use periodic evasiveness instead, then you get trouble, because the probabilistic method is a counting argument. You have to count how many subspaces there are. For periodic subspace, there are too many, but because we use the finer notion of BTT subspace, there are not that many subspaces we need to count. So this guarantees the existence. So this is the idea for the better construction. And then we are done. And here's the summary. We first construct the preliminary subspace using AG code with subfield evaluations. Then we construct BT evasive subspace and restrict the message space to it to get the final code. And this BT evasive subspace W is constructed using repeated composition of the construction from Goswami-Kobati paper, and inner subspace that is found by brute force search. And I want to remark that this repeated composition structure also appears somewhere else in coding theory in TCS. For example, in coding theory, there's a well-known construction of so-called asymptotically good codes that can be obtained by using this repeated composition. Another application, another place where this appears is the original proof of the PCP theorem. If you remember, they compose outer codes and outer PCP with inner PCP, and so they first applied outer PCP twice, and then use the inner PCP that has constant query complexity. So I think the proof structure that we use is very similar, although our proof is much simpler. But I think it's interesting to note that this structure appears in other places in TCS. Okay, so let me conclude the talk with some open problem and directions. So the first open problem is how to reduce our list size from exponential to optimal or even sub-exponential in no epsilon. And I want to remark that for explicit codes, the best known bound for explicit capacity achieving codes, best known bound is achieved by Fourier-Solomon codes, and it's already exponential. So it seems that we need new ideas for this problem. And the second open problem is that here, for our code, we achieve the list coding capacity 1 minus r minus epsilon, but the alpha byte size is exponential in 1 over epsilon. So if we want the really absolute constant alpha byte size q, like q equals 2 or 3, then there's also list decoding capacity, but we have to be more careful here. The list capacity is known to be inverse of so it's known to be HQ inverse of 1 minus r, where HQ is the so-called quinary entropy function. And the question is how to, if it's possible to achieve this capacity for absolute constant q. And this is wide open. I do not know any explicit construction that achieve this, or getting close to this. And third question is our methods also useful for constructing other pseudo-random objects. One potential application we have in mind is the so-called lossless dimension expanders, constructed by Guzmami and Rich and Xin, and their method uses this decoding framework. So we wonder if our methods are also useful there, and also maybe in other places. We don't know. So that's the end of talk. Thank you for your attention.
Thank the speaker. And there's time for questions.
So I have a question about the first open problem, so reducing the list size. So if you don't insist on this kind of optimal distance rate trade-off, is that easy to get? Or with what kind of trade-off can you get it? So if I insist on a kind of a poly 1 over epsilon list size, but I'm willing to live with the worst trade-off between distance and rate.
The optimal list size guaranteed by the non-existent code is just linear in 1 over epsilon. So the question is,
epsilon is the gap to capacity. I mean, if you say you want it to be poly 1 over epsilon.
Right. So, but say the
poly n.
I was thinking like the 1 minus square root r that you had in the.
That achieves constant. If you back up, if 1 minus c times square root r, it's some constant dependent.
I see.
I want to remark that for the second open problem, there has been a breakthrough just in this Fox.
Oh, I don't know. Okay.
Yeah, I didn't know either. I just heard the talk yesterday. So there was a paper about unique decoding, very close to Gilbert-Varshamov. And apparently they managed to do also list decoding very close to capacity.
With they, or what is the?
It's a Madhu Tulsiani and others.
Oh, okay.
And I think originally they could only decode up to the Gilbert-Varshamov, but till the conference they managed also to list decode very close to capacity.
So it's not for capacity achieving code, right? It's like
no capacity, but it's very close. It's like the codes of Tashma, the epsilon balance codes. They can decode.
I saw this paper on archive, I think. Yeah.
What?
I saw the paper on archive, but I didn't.
Yeah. So they can also list decode very close to capacity.
But the original result is just the codes that get unique decoding up to the Gilbert-Varshamov.
Yeah, so there was originally a construction of Tashma that was just an explicit construction of codes very close to Gilbert-Varshamov, unique decodable. Mm-hmm. And they didn't have even efficient decoding. And then in this Fox, there was a paper that got efficient unique decoding, mm-hmm. and they also got list decoding.
But I think that there was an older paper by Venkat that did it with very low rate. So here is this for arbitrary rate or for only some?
It's for rate very close to capacity. So the capacity is roughly say for binary alphabet, it's roughly half minus epsilon versus epsilon square.
Yeah.
So they maybe do a distance half minus epsilon, and the rate is epsilon to the 2 plus delta for arbitrary small delta or something. I think it's pretty exciting.
Yeah, sounds very major. No, I'm trying to recall how this relates to there was Venkat had an old paper that managed to get something.
The triply exponential in epsilon, something horrible, yeah.
I see. No, but I remember something restricted to very low rate, like very low constant rate. So, I mean, something that...
Yeah, I think it was like a half minus epsilon versus triply exponential in epsilon or something of that sort. If I remember correctly. Okay, no, you could do also... Okay, no. You could do... Sorry, that was not free. You could do epsilon to the 3 probably.
And what's the main ideas behind the new results?
So it's completely different techniques. So it's basically a graph-based construction. And the decoding is based on a unique gain, sum of squares, completely different techniques.
Right, but Matthew said that now they have a new approach, which is much faster.
A new approach? Also it is Fox, or they improved again? Or?
No, somebody asked him and said that now you can do it in quasi-linear time.
Wow, okay. They are very fast. Okay.